All right. Hi, class. I hope you all are doing well under the circumstances. I haven't gotten too much feedback about how these videos are going, so please do drop me a line to say, whether or not the audio quality is good enough, whether or not the recordings are clear and that you can watch them. If I don't hear from you, I'll just presume things are okay, and we'll keep going in this way. All right. So last lecture, we gave an overview of kind of where we're going to be going over the next couple weeks, which is to consider questions of mass equilibrium, essentially employing the tools of thermodynamics to understand where atoms and molecules go, how they distribute themselves. The first topic along these lines we'll consider in detail is that associated with phase transitions, or which phase of matter do molecules distribute themselves, and what are the underlying thermodynamic rules for how those choices are made. So we ended last lecture with a little bit of a discussion about what phases were, introducing this idea of an order parameter, which is a parameter that distinguishes two phases. And we're going to continue that discussion in this lecture today, continuing kind of an overview of different sorts of phase transitions to give you an idea of the scope that such a discussion could take. And then we'll end this lecture with some actual calculations employing thermodynamics to understand some consequences for phase transitions, or some constraints that we can put on what can actually happen. All right, so picking up where we left off last time, we were actually talking concretely about a specific phase transition, one we have common experience with, namely the freezing transition. And a question that we kind of were pondering was, what fundamentally distinguishes a liquid from a crystal? Another way to say that is, what is a good order parameter for this transition? Now, I'll remind you, a phase diagram which summarizes which states one sees as functions of, say, thermodynamic variables like pressure, I'll put on the y-axis, and density over here on the x-axis. Now, a freezing transition is one I can trigger often with pressure. If I take a liquid over here and pressurize it, increasing the density, well, most substances will abruptly change from some low density liquid to some high density crystal. This would be at one temperature. I could do the same experiment at a different temperature. Maybe the abrupt transition between liquid and crystal happens at slightly different densities. But there are a locus of these points where I see this abrupt transition that separate regions of thermodynamic parameters where liquids are stable from where crystals are stable, with an intermediate regime where we have liquid crystal coexistence. So over on this side, if I looked at my system, I would see a liquid. Over here, I would see a crystal. In the middle, I would see both. Okay, so what is a good order parameter? We started kicking around some ideas last time. We noted that while the density is something that often differentiates a liquid from a crystal, it's not really fundamentally important, because we know, for example, that some crystals are more dense than their liquids, some are less dense. So a crystal, the density difference is something that could have either sign. So that doesn't seem the most important, the most fundamental difference. simple, other thermodynamic quantities like the entropy and energy, well, those are harder to measure, and often correlate with liquids and crystals, need not be the same either, need not have a definite sign. And we alluded to last time something which was fundamental, which was a symmetry that is lost when we go from a liquid to a crystal. So let's explore that a little more concretely. Let's imagine I have a box. Whew, I love that I can fill with some substance, and I don't know if it's going to be a liquid or a crystal. Well, if I was going to try to figure that out, one thing that I could imagine doing is taking a thin slice of material and asking, when such a slice, what is the density on average? So I'll take a slice in the x direction. This row of x will be the average number of particles per volume. That's what I mean by density in a microscopically thin slice. Okay. Now, what would I expect to see in a liquid? If, for example, I plot that density as a function of x, well, the density of the liquid at one point in space and at another point in space in a microscopically thin slice will be the same. In fact, if I do this throughout this region x, I'll get exactly the same results. It'll be just whatever the bulk density of that liquid is. A way of saying that is that the density is uniform. We know that that must be true for macroscopic reasons, that, for example, liquids and vapors, both fluids, fill the volumes of their containers. They distribute themselves evenly. Now, if I contrast that with what I would get from a crystal, well, a crystal is something where atoms and molecules take up periodic arrangements. They are in very specific locations in space and not in others. So if I was to take this microscopic volume, say at the origin, well, maybe there's not a particle there. Maybe if I went a little bit further, well, then I would see some density. That would be coincident with some lattice plane in which the molecules arrange themselves. Again, microscopically, there'll be a region where there's no molecules, and then maybe another region where there is, a region where there's not. And this would periodically continue throughout that extent of the crystal. So crystals take up very specific lattice positions. In terms of this density, the microscopic density, where particles are, there's a fundamental difference between liquids and crystals in that liquids are uniform, particles are equally likely to be everywhere, whereas crystals have very specific locations. A very fancy way to say this is that crystals exhibit a loss of translational symmetry. Where in the fluid, I can be anywhere. I have a symmetry associated with different positions, moving to different positions in space. Crystals, by contrast, because they were only in very specific locations, have a lower symmetry, there are fewer ways that they get to distribute themselves because they are periodic. Okay. Now, that can, this is kind of maybe hard to visualize. So I pulled up a little movie, a little simulation that we can study. Where did this go? Let me pull it up. All right. So here's an example of a collection of water molecules where the oxygens are in red, hydrogens are in white. This is a simulation. And what you can see is down over on the bottom left, molecules are disordered. This is a characteristic snapshot of a liquid. Over in the top right, you can see molecules are at very definite positions. Those are the lattice positions associated with the crystal of ice. Now, just for fun, we can actually play a little movie to see how ice grows. And what you notice is that molecules indeed in the liquid can distribute themselves pretty much anywhere. There's a uniform density on average. Whereas in a crystal, there are very definite positions, very definite locations in space where particles are. And so indeed, there's a symmetry associated with uniformity, being equally likely to be anywhere in space, and that symmetry is lost as the liquid transforms into the crystal. So we would say that either translational or rotational symmetry is an order parameter for a liquid crystal transition. Now, you might say that this is similarly difficult to measure, but actually this is measured all the time. If you shine light on a material, if it's solid, and that light, it has a wavelength, which is coincident with the periodicity of that lattice, you will see very sharp diffraction peaks. X-ray diffraction is, of course, how you determine the crystal structure of some solid. Okay, so let's continue on kind of surveying different sorts of phase transitions. Let's consider another one that you all have common experience with, a so-called miscibility transition. This is, for example, a transition which separates two fluids, say water and oil. Water being one phase, and the oil then that sits on top of it, a distinct phase. Now these are distinct both in the arrangements of their atoms. Water being formed out of H2O arranges itself very differently than some oil would, maybe of some hydrocarbon compound. But also in composition, there's a distinction between the oil and the atoms that make up that oil and the water and the atoms that make it up. Now, in that oil phase, a reasonable question or something we should consider is this pure? What do I mean by that is that if I were to measure the composition in some small region of space in the oil, would I only find hydrocarbons? Would I only find oil? No, actually there is some chance that there is some water. Water is miscible in oil, just not to a large extent. It's not miscible, but there is some number of molecules which will be in that oil at any given time. It's not miscible in all proportions, but there is some amount which is miscible. For that reason, we can draw a phase diagram that, as a function of temperature and composition, say mole fraction of the oil, which goes from 1 to 0, well, we could ask, say, over in the water or wet phase, differentiated that from the oil phase, how much oil is in the water phase and how much water is in the oil phase. And in general, there'll be some amount. Say, at this temperature, there is some mole fraction X star of oil, which will be soluble in the water phase. Analogously, there's some amount of water soluble in the oil phase. Now, you all probably have some common experience that shows that if you heat things up, there's typically more mixing. So those mole fractions would get closer together. And very generically, if I go to high enough temperature, there'll be a region where water and oil are miscible in all ratios. So this should remind you a lot of the liquid vapor phase diagram we showed earlier. I have a wet phase, I have an oily phase. If I prepared the system down here, well, I would see coexistence, an interface between water and oil, whereas if I prepared the system over here, or over on the oil phase, I would see those two pure phases, but there is a temperature, we'll call this a critical point, beyond which I can mix water and oil in all proportions. Now that's an example of miscibility for typical fluids, typical liquids. The same sort of thing happens actually in our cells. Or more specifically, in lipid membranes. I could imagine, for example, making a membrane with two different kinds of lipids, say the white and the black. I could, at some temperature, form a little bilayer from these two kinds of lipids. A bilayer is just a little sandwich where lipids cluster together with their heads pointing their tails in the other direction, and then form a little sandwich like so. Let's see if this will work. Can I make this bigger? No. Okay. So at some temperature, it might be the case that those lipids will be well mixed. If I look at a specific part of the membrane, I'm equally likely to find the black lipid and the white lipid. But generically, if I cool down this system, what I would expect to see is a phase separation whereby all one type of lipid clusters together, excluding the other type. That is exactly synonymous with our water-oil mixture that spontaneously phase separates. Now, what is, I think, incredibly cool is this sort of thing can actually be imaged. So, segregation of phases with different lipids, It's not so easy to do an experiment on a bilayer, but what groups around the world have done in the last few years is prepare so-called lipid vesicles. Which is a lipid bilayer folded up on itself to form a sphere. So in the sphere, at some scale, we would see, oh, I can even do this. Let's do gray. Lipids equally distributed in themselves, well mixed. And if we cooled it down, what we'd see is big domains formed of each individual single component. Now, mind you, this is a slow process, just like oil and water separating. It takes time. And what we're likely to see at intermediate times are little droplets of one phase as they begin to grow into one big macroscopic domain. And so there's a group at the University of Washington led by Sarah Keller, which have actually made measurements on this sort of system. So here's an example of one of those vesicles. This is called a giant unimolar vesicle, blah, 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 giant vesicle. And her student, for example, Aurelia, in this case, has done microscopy whereby she's put in a little fluorescent molecule, which preferentially likes to be associated with one of the two lipids. This is the grayed image where the lipids are equally distributed everywhere. But as she cools the system down, oh, isn't that so cool? You start seeing phase separation between the two components. The dark lipids, where the chromophore, the fluorescent dye, is being excluded, and where the light is coming up, those white lipids, those are where most of that fluorescent chromophore is being sequestered to. Let's watch that again. So it's cooled down, you start to see phase separation, little droplets of one kind of oil in a sea of another kind of oil. All right, and there's so many more. Another very practical phase transition of a lot of importance is a so-called liquid crystal transition, which are made out of rod-shaped molecules. They can find themselves in a variety of somewhat exotic phases. So here's some rod-shaped molecules. They can be packed around in a number of different arrangements. If there is no order in either their centers of mass or their directions, you call this phase isotropic. It's like a liquid of rods. At higher densities, liquid crystals will point all in the same direction. Forming a so-called nematic phase, where rotational symmetry is lost. And if I increase the density even more, well, the molecules still point in the same direction, but now they stack in layers, forming a so-called smectic phase. Where both rotational and translational symmetry, or both rotational and translational symmetry, is lost. And there's a whole host of other transitions you might have heard about, things like superconductivity, for example. Magnetism is a kind of phase transition. They're responsible for your fidget spinners and a whole host of other things. And so what we're going to try to do now is to find some unifying principles for all these sorts of transitions. Essentially, the most basic question we could ask is, at a given temperature, pressure, and say composition, as denoted by some mole fractions, the simplest question we might want to know the answer to is which phase is present. So I fix the temperature, I fix the pressure, I fix the composition. Which phase do I see? And we already know how to answer that question. It must be the phase with the lowest chemical potential, because otherwise mass would spontaneously flow to the other phase. So let's think of an example. Water at 1 atmosphere of pressure. Okay. At 1 atmosphere of pressure and a temperature of 25 degrees C, which phase do you expect to see? So two I might consider are, say, the liquid and the crystal. And at 25 degrees C, we know water is liquid. So the relationship between these two chemical potentials must be that the chemical potential of the liquid is less than that of the crystal. At, say, minus 10 degrees C, that relationship is inverted. The chemical potential of the liquid is greater than that of the crystal. If we prepared a liquid and cooled that liquid down to below the freezing point, which is at 0 degrees C, molecules will spontaneously move from the liquid to the crystal. Now, what about at that melting temperature? What is the relationship between the chemical potentials? If I prepared a liquid, would molecules spontaneously move from the liquid to the crystal? What about if I prepared a crystal? Would molecules move in reverse? No, in fact, on average, molecules don't move either direction. And that is because the chemical potentials at the melting temperature are equivalent. Now, we were just manipulating the chemical potential by changing the temperature. So it's important to be able to ask, what do these chemical potentials as functions of temperature and pressure look like? Or just for simplicity, as a function of the temperature. All right, so let's try to make a plot of the chemical potential versus the temperature. An important point will be 0 degrees C. Well, what do we know? A chemical potential is the potential for mass flow. The temperature is the potential for heat flow. We're essentially asking how two potentials relate to each other, and we know that the equation to consider to sort that out would be the Gibbs-Duhem equation. Which says that S times changes in temperature minus V times changes in pressure plus N times changes in chemical potential are equal to 0. At fixed pressure, that term goes away, and I can rewrite this as the change in the chemical potential with temperature at fixed pressure is equal to minus S over N. N is a strictly positive number. S, the number of microstates, is a strictly positive number with a minus sign, must mean that that derivative is strictly negative. All right, what about the second derivative? How the chemical potential changes with temperature twice. Well, that's just minus how the entropy per particle changes with temperature at fixed pressure. Now, temperature and pressure are being manipulated here. One is being held constant, the other is being changed an infinitesimal amount. This is independent of the scale of the system, so it is implicit that N is being held fixed as well. We could pull that out, and what we're really asking for then is how the entropy changes with pressure at temperature at fixed pressure, which is a relationship between conjugate variables that we know has to yield this derivative being overall negative. So the chemical potential is a decreasing function of temperature with a negative curvature. So if we were to, for example, make a couple of these curves, let's say that this is the chemical potential for the liquid, decreasing negative curvature, albeit slight. Maybe this is the chemical potential for the crystal. This is so useful. Oh no. Okay, we'll just draw this back in. All right, at 0 degrees Celsius is where the chemical potentials are equal. That's this point here. And the phase that wins, the phase that's stable, the phase we see, is that with the lowest chemical potential, which means that at lower than 0 degrees C, we're going to see the crystal. And at higher than 0 degrees C, we're going to see the liquid. And so the chemical potential of water is something that exhibits a sharp kink at 0 degrees as it transitions from the crystal to the liquid. Okay. So generically, we would say that coexistence, where we see both liquids and crystals, requires equating or equality between the temperature, the pressure, and the chemical potential. It's at this point here, the temperature is the same, the pressure was being held fixed, so it's the same, and as a consequence, at that point, at coexistence, the chemical potentials are also the same. So generically for two phases, say alpha and gamma, This occurs when the chemical potential of phase alpha at temperature T, pressure P, is equal to the chemical potential of gamma at that same temperature and pressure. That is the thermodynamic requirement for coexistence. Now, if we stared at that equation, that is a single equation with two unknowns, the temperature and the pressure. So the solution to that equation is not unique. It's given by some temperature as a function of pressure, or some pressure as a function of temperature. If we were to plot that in the temperature pressure plane, the gamma is stable over there, alpha is stable over here. This would be the line of coexistence. Where the chemical potential of alpha is equal to the chemical potential of gamma. So those sorts of lines are the general statements of where stability changes between two phases, alpha and gamma, and along those lines are where you have coexistence. That should remind you of phase diagrams you've seen before in the temperature pressure planes, say for water, where you see lines demarking where liquids transition to crystals or liquid transitions to vapor. Now you might ask, what can we say about these lines? We know that they're given by this sort of equality, but what can we say about their shape? Well, if there was a temperature T naught and a corresponding pressure P naught on that line, and if I change the temperature by a little amount, dt, and stayed on that line, it must mean that the pressure changed a little bit, say dp. If both of those points are on that line, so T naught, P naught, and T naught plus dt, comma, P naught plus dp, if both of those are on the coexistence line, then both are solutions to the equality of the chemical potentials. It must mean that as I go from T naught to T naught plus dt and P naught to P naught plus P dp, that the change in the chemical potential for alpha must equal the change in the chemical potential in gamma. Or that if I stay along the line, d mu alpha must be equal to d mu gamma. Now again, from Gibbs-Duhem, we have that the change in the chemical potential is equal to minus s, let's bring the n over to one side, dt, plus v divided by n dp. That's true for both phases. So this equality here, then combined with the Gibbs-Duhem equation, lets me uncover that if I look at the entropy per particle for phase alpha times the temperature, which I don't need to give a label to because the temperatures are equal for both phases, and I add that to the volume per particle for phase alpha times changes in the pressure. Well, for phase alpha, that must be equal to that for phase gamma, namely the entropy per particle for phase gamma times dT, plus the volume per particle for phase gamma dP. So again, from this equation with the Gibbs-Duhem definition for the chemical potentials, I find this equality. Rearranging this, I could bring the dP's to one side, so I'll have V over N alpha minus V over N gamma times dP. I'll move the dT's over to one side, so I have minus S over N gamma plus S over N alpha dt, or finding the slope of that line, I find dP dt, the slope of the coexistence curve, is equal to the change in the entropy per particle of gamma less that of alpha, divided by the change in the volume per particle of, again, gamma minus alpha. So in fact, if we know how the entropies change between two phases, say alpha and gamma, and we know how the volumes per particles change, again between gamma and alpha, we can predict what the slope of the coexistence curve is. Let's try it one more time. Haha. This relationship is super useful. It lets us either predict the slope of the coexistence curve, or if we know the slope, predict the changes in the entropies relative to the changes in the volume. So this is known as the Clausius-Clapeyron equation. Okay, so that's what I wanted to tell you about today. So again, we finished kind of an overview of different kinds of phase transitions. And now you've seen how we can actually employ thermodynamics to discuss them quantitatively, arriving, for example, at relationships that must be satisfied for coexistence and constraints or equalities that tell us how those coexistence curves change. All right, well, I will now catch you on Wednesday.